Inclusive, eu vi um artigo na Wikipédia fazendo referência ao YOLO Live Once. E tem 23 referências.
Mas eu não sei. Peraí, de onde vem isso?
YOLO é uma brincadeirinha entre adolescentes americanos.
Pera, é uma música dos Strokes, né?
Nossa! Não, é uma hashtag
surgiu daí. Não, mas
tem múltiplas referências culturais na cultura pop.
Exatamente.
Mas eu acho que começou com essa música.
Ela também associada a Mandopolis.
E é isso mesmo. Good morning, our data scientists. Here, today, Ricardo is going to present about object detections with YOLO. Ricardo holds a Bachelor of Science in Biomolecular Physics and a PhD in Physics from the University of São Paulo, with a one-year doctoral stay at Rice University. Also, Ricardo has developed a 2-year postdoctoral research in bioinformatics at Unicamp. His academic research was involved with diverse aspects of complex molecular systems, such as protein X-ray crystallography, molecular simulations, and parameterizations of force fields to reproduce specific interactions in protein folding conditions. Recently, Ricardo joined Experian DataLab team as a data scientist. Ricardo?
So, good morning, everyone. Today I'm going to talk a little bit about a method that is very useful for real-time detection of objects. It's called YOLO, you only look once. So to start the discussion, I just would like to give an overview of the different questions that we need to answer for diverse applications in computer vision. So at the first task, that is the simplest one, we need to get an image and identify which objects that image is, to classify what is that image. If it's, for example, it's a cat, it's a dog. So you only need to have the idea or to characterize the features to identify one object or the other in the image. So a next more difficult task to use in computer vision, that is the one that we are interested to talk today, is the object detection. So you have further than you have the classification of the object, you first need to identify the position of this object, identify where is the object in the image, since maybe you have more than multiple objects in the same image. And this is very useful for self-driving cars in many applications today in artificial intelligence. A third level of complexity for computer vision is called semantic segmentation. In this one, we are not only interested in to identify what there is, which object there is appearing in the image, but we also need to give a class of the object per pixel. So we need to tag each pixel by a specific class. This is very useful for estimation of, for example, by image estimation of areas, estimation of characteristics of the geometrical characteristics of objects. And another more complexity, we get another more complex level. We have one, we further than get the classification of each pixel of the image, we also want to separate different objects from the same class. Like here we have two ships, and we need to track each ship as a single individual. And even further step of complexity would be like, further than that, we could identify the specific object there. Like, even if it's disguised, we can identify with, for example, by the patterns of the face of someone, you can identify the ID of this person. So in the case of object detection, that is the second level complexity, the previous slide, we have two tasks to perform that. The first one is to explore the image with a sliding window or with some different algorithm that we're going to solve later, to try to identify the region that is the region of interest, the bounding box that encompasses this region, and with a criteria that this region has a high probability to have the object that we are interested in. So after we identify this region, we can now is just a step of, it becomes just a problem of classification. So I'd just like to give introduction of the different metrics that we use specifically in the case of images. That is a little bit different from the machine learning common metrics that we use, like precision recall. So for images, since we have the geometrical position of pixels, the neighborhood is important. It makes sense to have a metric to compute the superposition of the predicted and the annotated label, the correct response, right? To have an evaluation of how well our method is. So one of these metrics that is commonly used is called intersectional reunion, also known as Ricardo index, that you can compute the intersection area between your prediction and the correct label, and compute the full area encompassed by both prediction by both areas, and then you can evaluate how well your prediction fits to the correct response. And this is robust because even if you have a very large area that encompasses the response, the intersectional reunion will be small. But if you have a small region that is also be small, you only have this going up to 1. That would be the best result when you have perfect superposition of the area of the prediction with the label. Another method that evaluation criteria that is commonly used is called mean average precision. In that sense, would be the mean of the precision. So we can compute, since we can estimate a model that is able to classify many different classes. We can see how well it classifies for each class, and we can compute the average precision for that class, taking all the queries that someone gave to the model. And after that, we can compute the average of all averages in the classes, and then we can have the mean average precision. And in that case, what we say that is true positive is intersection over union higher than 0.5, and 50%. And we have two cases of false negatives. One would be like if you have a box that is not superposing well to the correct label, and then it maybe be a box in another place of the image, and since the intersection reunion is smaller than 0.5, then we understand that it's classifying something like, it's saying that it's a human is in a place that is not there, so we say false positive. In another case, we say that for a different class that is superposing to the region that we want, like if you take the box of a person and say that it's a horse, then you say it's false positive also for the horse.
I think that just to clarify, we have a two-step problem. One is to identify the region of interest and then draw the boundaries of the region of interest. And then after selecting a smaller region, we're going to classify an object or identify which object is inside the region.
Exactly.
So the first metric, the Ricardo index, is for the first part, to identify the region of interest. And then the second measure is to how well are we classifying the object inside the region of interest.
For different classes.
Yes. There is so let's Okay, great.
Actually, this metric is used here. So it's because to get the true positive, to say if a prediction is true positive, you have this as a criteria here.
Okay.
So it's like a further more general
Yeah,
metrics.
so in the case that you miss the region of interest, it's going to be represented in the mean average precision by taking a false
Yes.
as a wrong value.
Yes, for that class that you're measuring, if the box that you predicted has intersection over union lower than 0.5, then it's a true positive, a false positive.
Okay.
And another problem that is that we have for all this, it appears in all these methods for object detection, is the problem that you possibly would have many solutions for the same guy in the image. So you need to find a way to filter the one that is the most the best fit, the best guess. Right? So one method that is commonly used is called no maximum suppression. So the idea is that you take all the predictions that you have in the entire image, and then you take all the predictions for one specific class, like person, and you see for all those predictions the confidence of them. You sort the confidence of them, and then you take the highest confidence one as your reference bounding box, and then you compare with all the other bounding box the intersection over union, and then you give a threshold, for example, 0.7 or 0.3, and all the guys that have intersection over union above that, you just drop, and then you keep only the one that has highest confidence, and then you can remove the redundant bounding box.
In the case that we have more than one, I have two predictions that have high confidence and it's above my intersection of the union threshold.
Yeah,
What
like
I do when I have two possible as good.
They should be below the threshold to be maintained.
Yeah.
Below the threshold.
Because if they are above some threshold between themselves, then probably they are talking about the same object and they'll choose the highest confidence. If they are below some intersection threshold, then probably they are talking about different objects, and then you keep both.
yeah, for example, let's suppose you have like possibly you have a photo of that with two motorcycles, and then one of them is behind here, and then maybe you should have two boxes. But then if they are not superposing too much, like intersection over here of 0.5, then you accept them as two different solutions. But you use the confidence to sort the response, and you take the intersection over union to see which ones you're gonna drop. So just to also give the context of how that has been developed the computational vision field, because it's very recent, and then many of the solutions that have been developed in one research have been used in another ones, and then it's very progressive field. So the first methods that people have been using for object detection is called this hard features. So the idea is that you can take some patterns that you propose some patterns, and then you try to run in the image to find regions where this pattern matches very well. So the idea is that you have an ideal pattern that you have like a perfect gradient here, maximum gradient between two consecutive pixels. And then you have an image that is like this, a real image that's like this. So the idea is that when you superpose this matrix, this kernel, over the image, the matrix of your image, you can compute the number, the sum of pixel levels in the black part and in the white part, like here in this example, you can also have other patterns. And then if you compute that and the difference between the average value for the black part and the white part is 1. So you can say that you have a perfect match. Right? Higher values up to 1 are better solutions. So the idea is that you can use all these patterns, propose different patterns for different problems, and try to identify regions where your object should have a higher probability of being there. So application that became very famous for that is called the YOLO Jones. So they proposed the use of hard cascades in an algorithm to find faces, and it works very well. So you cannot find the identity of some person, but because we have this pattern of 2 eyes, nose, it's very easily identified by the hard cascades. So the idea is that you have some generic features of some kernels to filter the image, and then if you find these guys, you go to the next step, and then to the next step, and then you go refining up to you find all the features that give you a high confidence of having face in the image.
Sorry, but are you doing that at different scales? You do that in a coarse grain scale, and then you go.
Yeah, you can improve the size of the kernels.
Yeah, but I just want to understand what this animation is.
Yeah, you see that here you have kernels of different size. So
Right.
you can have like a kernel that's not. It's not necessarily bounded to 3 by 3 in the last like here. It's not necessarily like.
So it's like a mixture of kernels at several scales at the same time.
Yeah, like you have here a group of kernels, and then you pass all these kernels in different size. You
Different
find
scales at the same time.
different scales, and then you run all these different scales, and then you say, if you have a threshold that if it finds 3 different features at least one of the scales, then you go to the next stage, and then you keep going up to you at each step. When it advances, you increase a lot the probability of having the face detected. Yeah, but you see, possibly you can try different scales and different patterns. And then at some point, everybody was trying to propose very insights about different kernels for detection of different things. I think that I can talk about this. Another of this, before starting to talking about convolution, another different method for object detection that became very famous called the histogram of oriented gradients. So the idea is that you take your image and you apply a kernel to compute the gradient of that image to see how that changes. And you compute in different, can try different grids for different size. And then you can, by that gradients, you can compute the magnitude of vectors for gradients, right? And then the idea is that if you have a pattern of gradients that superpose well to pattern of gradients in another image, then you can match in a much more general method than just giving a kernel by hand, right? Just proposing the kernel. So the idea is that you take all the cells, you compute the gradients, and then you arrive with a matrix like that. And then in that matrix, you have some values that you can that give you the magnitude and the orientation of the vector. And then from that, you can compute, like in one of the coordinates, you can compute the angle. And then from the angle, you can populate a histogram. And then from that histogram, you can match with histograms from different images. And then when you have high match between them, you can say, this is a prediction. This is still very useful. Many people use that. Like people in the Asia, and then they use that for roof detection also. detection of textures in the roof.
Ricardo, in this case, you have to use gray images, or you have some way of dealing with the colors.
Yeah, it computes for each label, each layer. You can compute for each layer. So after this, I see that also here they proposed that in 2005, so it's not so long ago. So after the recent advance of deep learning, so people start to say, oh, why not? We should not use deep learning to propose for us the features that we are not good enough to identify. Right? So the idea of convolutional neural networks is that you have a multi-layer neural network, but it's based on the idea like in our eyes, you have many sensors for each region of the image, and then the sensors, they start to convolve in smaller sets, layers with smaller sets of neurons, up to they somehow encode the information that you see that goes to our brain and makes us interpret some image. So the idea here is that you have connections that are not fully connected. So you have connections that are dense in the region. So you see that this guy, he connects to this one, and this one, but he does not connect to the further ones. This guy connects to these ones that are neighborhoods, but does not connect to the last ones in the end of the layers. So the idea is that you compute the region of pixels, the
Correlations are always local.
are local, exactly. You compute the correlation between them, and then you can get some local patterns, like some patterns for the specific region of the pixels of the image. And then when you convolve that, you also can get the patterns that are in a bigger region, like you can identify faces, and then when you go further, embedding this information, you arrive at the point that you can see patterns of context, like if it's a full person, and then you can classify objects. So the main, let's say, rule for that is that if you encode too much, then you can have a lot of idea of the context, but you don't have idea of the fine details of the image. But if you encapsulate just a little, then you have details of the region like texture, but you don't have details of the context for classification, for example. So for that, we use some here, just showing some very common layers, common applications to common pieces to build the neural networks. So basically, you have a layer that's called convolution layer. That you have some filters, and you can stack many filters in a row, and then you can take your pixel, and then you can apply these filters with these kernels that takes your region of your image and then multiply neighborhood pixels, and then you arrive with some final value. And then here I'm showing like this layer in the outer part is called the padding. So here we have a padding that allows to not lose the size of to not decrease the size of the matrix. And also we have another method that's called pooling, and the most used is called max pooling. So the idea is that you can convolve your image to take the details of the context and to encapsulate that. And like in the max pooling, you take just the highest value. Like if you take this one, take the highest value, this one, take the highest, and then you arrive with this value. And you have also the process that is the reverse process called unpooling, that is useful when you need to deconvolute your image to get the original image tagged by like semantic segmentation. And also something that is very important for the models is the activation layer. when you apply convolutions, and then by these multiplications you get some values, and you need to decide what response, which values will go forward in the network. And then we have the most common sigmoid activation function. ReLU is very common also used, and now we have recently some different activation layers called functions called like leak ReLU and LU that they improves the process of conversions. And also, usually in the end of the neural networks, the convolutional neural networks, we have a function called softmax. Not necessary, but the idea is that if we have many classes, we need to decide which one is the most likely to be the correct one. So you can take all the final values for the final layer, and then you can compute the normalization to get the probabilities of each of the classes. So here, if you have like classification, you have only encoder. If you have object detection, you have also encoder, but not fully encoded, right? You have a tensor that is not unidimensional. And you have also, when you have segmentation, you also need the coder part to see the response of the predicted labels for each pixel. So these are the precursors of the YOLO. So they influenced the YOLO development. So the first one's called methods called region CNN. So the idea is that we have that problem of looking with different sizes of kernels, looking the image to find where you have the region of interest, and how to do that in a very effective approach. And after that, how we can classify with very accurately classify that region about the class, right? So this first method, what it proposes is that you take methods called selective search, and this method basically it takes your image, you generate many bounding boxes, and then you take by this bounding box, you see the superposition of them, and then you compute the gradients of the image, like you doing like a very coarse segmentation by gradients, like by different textures in the image, and then you can merge the boxes that are in the same region of the segmentation, and then you can propose a bigger bounding box, and then you can filter the top 2,000. In that case, they use the top 2,000 guessings of the region of interest, and then you can put that in use that as an input in your convolutional neural networks, and after that you can predict the class of the final image. And then for that you need to resize all the images to the size of the input of the neural network. And after that, also you use the convolutional neural networks to generate the features. And in that case, they use support vector machines to classify based on the feature generated by the convolutional neural networks. And it works very, very well, but it's slow. So this is the selective search. So you have different levels of segmentation by textures. And by these different levels, you can find boxes that are superposed very well.
When you do the segmentation, that's unsupervised, right?
Yeah, this is just by gradients, like watershed. You just use some very coarse methods for segmentation, like you find regions that you have pixels with levels that are similar, and then you can use kernels with different size just to compute these gradients.
Okay, then you have several candidates for segmentation, for segmentations.
Yes. So you have some. have the segmentations by it tags, it annotate the regions, but then by that regions, if you have many boxes in the same region, then you can say, oh, I do not necessarily need all this.
But how you decide what's the appropriate scale to work? Because you can segment at several scales. So how do you decide which scale is relevant?
Yeah, they did. I think they tried with many scales until they parameterize based on the response of the.
It's a happy parameter.
But actually,
The final goal is to identify what the object is, right?
it depends. It depends on the nature of the picture, right? Some pictures are more.
Yeah, but the size of the kernel that gives
coarse
you.
than others.
Yeah, the size of the kernel that gives you how the level of merging of the sections you can change. Like you can parameterize that based on your data set. Actually, they did that already. They have the weights. They did that. They say, oh, we use the Vasco data set, this Vasco data set, Pascal data set. We use it all this data set, and then we parameterize that to work well on that set
So
of images.
they work on the assumption that all the images on the data set contain the same size, characteristic size in their segmentations.
Yeah, because these are images from daily life, not like images from satellites, not images from micro things. So it's the idea that they use like also ImageNet, so that they're images from the streets, images from the house, and then you have a certain pattern of dimensions that is common to daily life images. Yeah, so this problem, this method has a problem that you need to propose a lot of regions, and then all these regions need to run in the convolutional networks to generate the features, and then run a SVM classifier, and it takes a long time. And then for each run, for each image, it takes like 47 seconds in their benchmark. And the selective search is also something that as we told before, you need to set that for your data set, and that is not something that is changing automatically, right? So the same guy, he proposed a better solution for that to try to improve the performance of RCNN. So the idea is that instead of using the feature selection, the method to automatically identify the boxes, you use convolutional neural networks also to generate the regions. And then by that regions of interest, so he gave the response for that to train the image to identify these regions. And then after that, you pass through a fully connected layer. And then with this fully connected layer, you can predict the bounding box, and you can predict the class of the image. And that increases a lot, but you still have, we have here including region proposal, excluding region proposal, you see a very high difference in faster RCNN. So you see that the part of giving the regions is still the longer part of the model, right? And it takes like many hours to train in the data set. So finally, then at the same year, the 2016 was when was proposed the fast RCNN. This guy Joseph Redmond, he proposed the funny guy. he proposed a new architecture that instead of having a convolutional neural network to propose the region and another one to classify that, you can run everything at once. Right? So the idea is that you take your image, you can break your image in a grid with many cells, and then for each cell, you can give the task to identify an object and classify it. So you can generate many boxes, propose many boxes from using a convolutional neural network also.
Coupled to the grid or not necessarily?
So for each of the cells, you can give, let's say, five bounding blocks. So each cell, we generate 5 bounding blocks that are not restricted to the size of the cell. So they can go further, and they can be very big or very small. And your set will make the bounding blocks converge to a specific ratio for class. So the idea that you give this freedom restrictions, this freedom degrees for the system to try to adapt itself, and then it predicts the region that is. You have to perform 2 tasks at the same time. It predicts the region that you have a high probability to have an object, and also predict the class if that region has an object. So in the end, if you take the high probability of having an object and high probability of being a class, then if you multiply them, you have a metric for the high probability to have the object that you are interested.
Just a comment. This seems to be a trend in connector architectures recently to try to predict a lot of things and join prediction at the same time.
Yeah. And also that allows you to avoid overfitting.
Yeah, it's like a regularization also.
Yeah. So the idea is that you have many scores that you need to compute. One of them is how can you find an object for the CNN? Oh, how can you find an object in this region? So it takes one cell, propose. And then you say, oh, this has a probability of 0.7 to have an object there. And then if that is an object, with that restriction, what's the probability of that being a bicycle? And then it's a proposed probability. And then by multiplying this probability, you have a confidence for that class in that region. Here, I think that would be more clear. So like we have an image, and then we take this cell, from grid, and then if the box that we draw is always inside the cell. So if the box has the center inside the cell, the object is also inside the cell. So that cell is the responsible for doing that prediction. So each cell only predicts one object and one class, with the class with highest probability.
But the opposite also. Any object is only predicted by a single cell, even if it's contained in a lot of them, because its center is in a single cell.
In the end, yes, because you can have, like, you would have another cell here with bounding box that could take the guy, but at some point it will use the max expression from the first slides to decide which one you take. So you can have different cells predicting the same guy, but at some point in the end of the method of the process, you decide which one is the best guess. So then after that, you can, like here you have 2 boxes for the same cell, and by the intersection over union of these 2 boxes, considering that you have an object, you have probability of being an object, probability of being a class, and if you do all these probabilities and multiply them by the intersection over union, then you can decide which solution is that has the highest potential. So here's the thing that you decide. So you can have 2 predictions for the same guy. Here, the predictions has been kept because the intersection over union is smaller than 0.5. So this is a case that you can have 2 times the prediction of the same thing, but this is rare when you apply it to the daily life method. So so this is the architecture proposed for the first YOLO. So you have 24 convolution layers, and then you have 2 fully connected layers. So these convolution layers, they take the context of the regions, encapsulate them, and then in the connected layers you have, it performs a regression, a linear regression to find the best solution for the bounding box. And also these layers, they are responsible for doing the classification. So I think that here it makes more easy to understand. So in the end, what we need to solve is this tensor, right?
That's the output tensor.
Yeah, that's the output tensor. So the S is the number of grids. So you have grid that, in that case here is 7 by 7. And you have the number of proposed box times 5, y times 5, because you have the bounding box score, the confidence score. You have the x and y positions. That means the relative position of the box in the cell.
That's probability matrix on how probable is the x coordinate, or what's the content of this x in this z-axis? What's the content of the x value
In here?
No, this. Which?
Oh, here.
You have x and height and width of the image. Then you have the z-axis as all different classes and other information that we're trying to predict. But what the content of the matrix S by S with height and width, but at the x index.
So here's the probability of having an object.
Okay.
Here x and y are the positions of the center of the bounding box in the cell. So you train your system to identify which parameters give the best bounding box considering aspect ratio and size for the object.
But when I submit an image to the YOLO network and I get this tensor, the X matrix is going to be just a 0-1 matrix between if it is or is not the center of the image, or it's going to be a probability matrix where the network believes is the center.
I think that maybe that will make it more clear.
My question is, after that, I'm going to.
So this is the annotation. Like if you're gonna annotate a new data set to customize and to identify the thing that you are interested in. In case you want to identify risky labels for risky, dangerous chemicals. So you can use any method to label that you want, and then you can label the class, you can label the position x and y, and the dimensions width and height, right? And then you can take that input in the YOLO input format. The idea is that also you take this x and y, and then you normalize that by the size of the cell. Here's by the size of the image, but it breaks in cells. And you also normalize the width and height by the size of the width and the dimensions of the box. So when you give the label, you try to adjust these 4 values: the x and y center in the cell, and the width and height of the box, and all then are normalized. The width and height by the size of the image, and the x and y by the size of the grid. So they all then are between 0 and 1. So they are there. These are the guys that are there in the tensor, right? So this first part, it goes. I think that maybe. Oops. Sorry. Okay. So you have x, y, the positions of the center in the cell, the size, the ratio of the image, and you have that for as many boxes that you want to propose, and you have the prediction for one of the classes. So if you gave there the class 0, if you put here 0 for dangerous signal. There'll be 1 there in that bin, right? So you have let's say one unit tensor for each of the grids, each of the 7 grids. So the idea is to minimize the full tensor in one stray trading.
I think it's very strange that they first put a dense layer breaking all the spatial relations, and then they create the spatial relations again, making a cubic tensor of grid size. I don't know why they do this. It seems very strange, doesn't it?
You mean like because it's a cubic tensor?
Yeah, because, well, you usually use the convolutional neural network to keep information about the spatial relations. So, but the next to last layer, you break this. You make a dense layer, and then you create again a new tensor. How make the spatial information be encoded in the dense layer? It's not clear.
Yeah, I think that the part of the context and the part of the, like, to identify which of the objects is there, that the class, the object, is being encoded here. And then when you arrive here, you just need to adjust these guys. Right? So here you already have the dimensions of the grid. So you just need to adjust these 4 guys, and you adjust that. The fully connected dense layer is responsible for adjust the boundary box, the parameters of the boundary box. And then when you give the label, the tag, if you try to find, let's say, if you see that always a person has a aspect ratio of 0.4, and then you set the dependence of W in age.
But if I believe that different images may have a different number of bounding boxes. Maybe if it's just a cat and a flower, I have 2 bounding boxes. I can submit, but I was just wondering how do I work with a flexible and cubic tensor? Am I saying something wrong? Or because if I have in one image 2 bounding boxes, I expect this block of B box 1 and B box 2. But let's say that I have 5 bounding boxes, I have a longer tensor.
Usually, like if you have more bounding box, you have the higher probability. Like for the same grid, if you keep the grid constant, if you increase the number of bounding box, you have many solutions for the same guy. Right?
So usually I always have a tensor with the same dimensions, but I have duplicate solutions for an image with less objects.
Yes. So like the 2 methods to regularize that thing is if you decrease the number of grids, the dimension of the grid, like instead of 7 by 7, you decrease to 3 by 3, and then you increase the number of bounding box. It can compensate if you have a lower number of bounding box, but you have a higher dimension of the grid.
But so with this tensor dimensions, I will have like a selection process to exclude some solutions after.
Yeah. So you take the one that has the
Because you could have S squared bounding boxes for a single image.
Yeah.
At least.
You use this guy based on your loss. You use this one to select which one. But for every cell, you have only solution in the end.
Okay. Yes.
And between this bounding box, so it will compute for all the bounding box that you proposed, but at the end, it will filter the one with the highest probability. Yeah, like if you have 2 here, but you could have any, it will take the one with this, where this is higher. Bounding box confidence score. So just to take an overview, so you take the image, in YOLO it computes the grid, generate the using the cell, it centralized a bounding box there. So for each cell, it has the task to propose a solution. So you can give many bounding box for them to many attempts that can try. And then for all this bounding box, you have the dimensions of the bounding box that are being solved and are being optimized based in the solutions that you're giving to train. You have a confidence score that will allow you to choose which one is the best solution. And also you have a probability for each class that allows you to choose the one that is highest. You can have the probability for everything. So you have probability for car, for person, then you can choose the best solution. Then you can try that for S by S cells. You can decrease the dimension here, but increase the dimension here, or you can try vice versa. And this is the loss function. From this method. This is crazy. At first, I was trying to understand why it does not. So it have many parts. You have localization loss, confidence loss, and classification loss. But the confidence loss actually is a combination of this both, right? You could. I was thinking, why it cannot use just the confidence to identify the best solution. But I think that if you restrict the solution to be an object and the correct class, the convergence would be much slower, right? So if you train the system to identify an object, at the same time you train the system to identify a class, at the same time you train to identify an object in the class, correct class, then it converges faster. Yeah, so here the object loss is just you take the annotation, you have a combination of position in the cell and the dimensions of the bounding box, and then it always comparing with your solution, and he's trying to fit as similar as possible to the average profile of that object, and say that this is probably few of the features should be gradients, right? To identify an object, the silhouette. At some way it's encoded in the convolution. I think the convolution on the neural. So we have the confidence loss. So given that it's an object, so this is an if. So if it's an object,
Okay, you compute that.
you compute that. If it's not an object, you don't lose time computing that. Here also, if it's an object, you already computed there. You compute the class.
Why did he create this? Why you have another parameter behind? Because if you do not have the no object lambda, you could save one term. What's the purpose of this?
This is because they want to the weights, because there are many spaces without objects. If they didn't put that lambda there, the confidence would be very dominated by not predicting things, because it gives higher scores. So the no object lambda is actually much smaller. So it's more okay to try to predict objects where there is none.
Okay. So that's just to imbalance the terms that would be for object classification and non-object classification.
Maybe if you had images with lots of objects, this would be, the necessity of that would be minor, but in these cases, they were like 10 times lower than the original. Lambda is like 0.1.
Yeah, and also, so this is the idea that we had. I think that's that they did like some fine-tuning, a lot of time fine-tuning, a lot of attempts, and then they are arriving like a Frankenstein of the to propose the final model. Yeah, so the idea is that you can train the system at the same time. it will train how to find objects and how to classify them. And then when you train them, it's like a regularization. And if you multiply both, like if you have the confidence point bigger than 0.25, that'd be like 0.5 plus times 0.5, then you have a threshold to say, oh, this is a solution.
Ricardo, do you understand why he writes real confidence and a real probability? Because I didn't understand that when I was reading.
You mean real?
Yeah, because he's comparing
because
the real confidence
the real
and the real
confidence,
probability.
the real confidence and probability are one, because they are your label. Like the one in the risky, the dangerous sign. So you're given a label of one for both in that box.
They could spend some time making the notation prettier, I think.
And the advantages of the YOLO compared to another ones, that now you can run real time. You can run like 45 frames per second.
Wow.
So you can use a smooth tracking method for object tracking. And also the interesting thing that they found, as understood, they were not planning to have that, but the advantage of YOLO based compared to the other ones, that it also works for different, like if you have a painting, because the texture is different. Another methods will not identify the objects in a painting or in an artistic image. And the bad points, the limitations is that because you give the data set for the system to optimize the bounding box, you bias the bounding box to have the aspects of the objects that will be identified. So because they use a very common data sets for daily life images, you make a bias for the bounding box to be bigger than the grid, than the cell in the grid. So you have a problem to identify small objects, and also you have a problem to identify guys that are very, very near the image that you don't have. Probably this is probably because based on the data set that you choose. See, if you
So you almost fix an aspect ratio for a given object, and you are restricted to this scale.
Yeah.
But it seems to the limitation more general than just YOLOs. Like other applications, maybe they would have these limitations also.
Yeah, usually the neural networks that try to be a scaling invariant, usually they try a method called pyramid parsing. So like you take different scales of your image, like you scale your image many times, and then you feed at some point in another layer that is far from that one. And this is exactly what they did in YOLO 3. So just to contextualize, now they are in YOLO 3. They have had YOLO 1, that one that we just talked about. Then in 2, they added a batch normalization. That's
like 9,000.
9,000, because they trained it with 9,000 classes.
9,000 of common.
That's from ImageNet. And then and that one they add the batch normalization after each layer. And batch normalization, you try to decrease the difference between the values after the filter application, and that improves the stability of the net. And also after that they did this version 3, where you add this pyramid scene, this pyramidal transformation. So you have the convolutions like before, but then at some point you do the unpooling, so you increase again the image, and then you take the image and put again mix that with the previous image.
You have a residual connection.
Exactly, residual connection. And then you can have the...
It's like black magic. There's no food, and it's just
It's dark magic.
Lego blocks. And just play around until you find something interesting.
Yeah, it's like
It's not clear why it's so faster than the other
It's
one.
not science anymore.
Why is it? You know?
because you have only one convolution neural network. So you have this one, only one pass.
Okay.
So the RCNN, you need to try that for 2,000 guys. After selecting the 2,000 guys, and
Okay,
for
okay.
fast RCNN, you have a convolution step, and then you have a feature generation, then you have another convolution step. So this is, I think, almost like 10 times faster than fast RCNN and 100 times faster than the first RCNN.
So I was thinking that we can have like a YOLO trained for, like, if I was thinking about self-driving cars, so you can have like a close range YOLO and a long range YOLO, and you have both running in parallel, so you can mix the predictions, so I can see people in the background and see people in the foreground, and have like one YOLO. Actually, I am extending the purpose of YOLO, so having like a bigger network composed by multiple YOLOs running parallel with different object scales and
Like a fast YOLO to avoid hitting another car, and a normal common YOLO for planning your trip.
yeah. So I can. I believe that when you see that Tesla videos about their network classifying, you see like a very characteristic aspect ratio for people and other stuff. But then if you add a long range YOLO, you can like track people starting to cross the street in the end of the block, and have to, if your driver is in attention, take action about it.
And this is important because YOLO, you know.
And then that's it.
That's it.
It's very, very little time.
Thank you, Ricardo.